ready? Are you mad inside? Got you strapped down to your seats. Out of the doorway, bullets rip full clip. Guard speed approach, follow my lead. Fire winds gust, empire crush, full thrust. Falling the whole row with the rush. Untouchable chunk of an earwax assault. Sound wave slave out the back cave smoke. My belly full prance dance avalanche quote. Down slope, elegant ass fantasia. Killer whale tail in the hell, black male from Asia. All out the woodworks, hood shirts and wizards. No match, unhatched. The rapids rigid in the shaft. Shiny cop, hip hop to the limit. Night watch, path mark, spark, spin a quake, nuclear blast. Heavy on the cash, give it what it takes now.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
The diabolic witty dialect stalker in Gotham City, with the possibility to stop your walking ability. God forgive me, spark enemies with pistol grips. The missile tips impact hit you so hard, you official script strike with physical hits. You visible watch for the imperial blitz. Serious mid, subject to the wreck war tones. And door poems liver than WWF war zone. More component Gotti tracks, bodies collapse. Rap for lottery stacks, shatter like when pottery cracks. Logical facts from the terror dome. Spill from the guts, drill till you bust from where you bust. And guard you now we trust. Told you like Hounded mutts. Pound pump your sound struck clown what? You'll get drowned in the cut by crowd roundup.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
Hey yo, I spit bars, traveling tremendous speed, measuring far. Which what's in satellites, circling Mars. Verbal onslaught, bring forth physical force. Up 100 wild, pal in the Trojan horse. Thought method, set it on generic mic ethics. Professional next, left folks beheaded. This music is mind control like computer chips. Been doing this for numerous years, refuse to lose it. With jungle tactics, maneuver like a trained soldier. Hall of Fame, flamethrower, take aim, it's game over. Ayatollah, high roller, nine-toter, mind controller, 2009 time quota. My coalition, bring the demolition. Wu blade incision, slate the competition with no intermission. Spitting hazardous darts up front like Rosa Parks, make a million men march.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
Who got next? Meth got next, I chin check all these MCs, line them up guard, I go jihad. Declare holy war, it be hard to dip and dodge. Police squads trying to bogard, we rip and raw. The boulevard ain't safe for your kids, that's how it is. In the ghetto we ain't scared to death, but scared to live. So Goldie, mosey to the spot, get that moldy. Rusty ass 38 special, owe me. Slowly I turn, face the one and only. Naughty by nature, do my dirt all by my lonely. Ass pretty Tony, when I got up, keeps up. 36 chambers, enter at your own risk. Take that watch off and tuck your necklace. City never sleeps, streets is restless. Rap style will slay you when you least expect it. Pull a plug on your respirator, leave you breathless. Wu-Tang forever and a day better. On your boys, I deploy battleship raps, seek and destroy.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
All right, so another announcement regarding internships and networking with industry partners. We had the career fair last week, or was it 2 weeks ago? I forget now. But in any case, if you missed that, or even if you went, now is the time to go to this mixer this Connect to the Network. It's held exclusively for computing majors. Several of our industry partners will be there. It's this Thursday from 4 to 6 p.m., and that's in the Shore Center, which is on the south side of the stadium. Second floor, so you just walk in, go up to the second floor. Should be open. But otherwise, that's this Thursday from 4 to 6. So it's yet another opportunity to get your name out there to potential employers looking for that first internship, even after your first year or during your first year. All right, so we'll pick it up where we left it off. We were talking about functions, right? So just as a quick review here, since it's been a week, functions are reusable units of code, right? They have a signature, that is the return type, the identifier, that's the name of the function, and then any parameters or inputs that it takes. For example, over here, what we did was we built a library called utils.h and utils.c, and we placed, we made a miles to kilometer function, we made a round ascents function, we made an isPrime function. The signature for round ascents here is that it returns a double. Its name is round ascents because you name the functions what they do. And then its parameter list here is there's only one parameter and it takes a double X here. Right? That is ended by a semicolon and accompanied with proper doc style documentation here. Right? All of your prototypes are required to have doc style comments going forward. Right? All right, and let's see. Prototypes and documentations go in the header file. So we split these up into different modules, or we call them libraries in C. Right? The definitions go in the .c source file of the same name. So for example, over here, I've got utils.c. I included all of the libraries that, of course, I would use. I'm doing some math stuff. I'm doing some standard Boolean stuff, so I include those. But I also include my own header file. Again, that's a cut and paste. It's the preprocessor doing a cut and paste of all those prototypes up front. All right? And then I have the actual definitions. I repeat the signature, the name, the return type, and the parameters. But instead of a semicolon, I have an opening curly bracket, closing curly bracket that defines the body of the function. Anytime you call that function, that's the code that's going to get run, right? Before it returns from the function. Okay? You compile using the -c flag. So in this case, I would compile using gcc-c utils.c. You don't compile header files. Or, I mean, you can, but we're not going to be doing that. That produces a .o file. That's called an object file. Somewhere on the computer is a shared object file that has that stdio.o file, that math.o file, right, etc. But the compiler takes care of all of that for us. What we need to do is we need to say, well, use this file that's in the current working directory when you compile for an actual main. Okay? Now, functions are perfect for units for unit testing. And we went over what unit testing was, right? Where it's a proper input-output pair that is known to be correct. You've got input, you've got expected output. You feed that input into your unit, that produces actual output. Now you compare these two things. Do they match? If they're integers, are you asking, are they equal? If they're doubles, you're asking, are they close enough? Okay? And if they don't match, then the unit test fails. Otherwise, the unit test passes. Grouping many of those things together gives you a test suite, right? And it is repeatable and it's automated if you're using the proper formal unit testing, right? And we're just going to give you a preview of that here. Oops, I've got it formatted wrong there, but see Maka, there we go. There are many libraries that for C for doing unit testing, formal unit testing. The one that we're going to use in this course is called CMaka. It was originally a Google project called CMockery. Right? And so what does mock? Well, C obviously stands for C, programming language. But what does mock mean? Well, mock is fake, right? It's a mock-up, right? It's a fake data that you use to test your functions. It's not actually being used out in the wild. Instead, you mock up your test cases, right? And that's where it comes from. It's Maka now. When open source, they changed the name. I'm just going to give you a preview of what it looks like. Ahead next week, you'll be using this. It's quite complicated. It's a little bit complicated. It's too complicated for everything that we've covered so far because we need pointers and function pointers, which we'll get to by the end of the semester. So instead, we provide you with as much a starter code as possible. Basically, we've got our built-in tolerance right here, right? As a you know, if a double is within 1/100th of each other, then we'll say that that passes for at least for this application. We've got a function that determines whether or not it's close, right? Is the difference, the absolute value difference, is that within epsilon? And if so, then it's going to end up passing. The real magic is done way down here, right? Now, a preview of what you're actually going to be doing, you're going to be doing a bunch of functions that convert from certain colors. Like this week you're doing, in your lab, you're converting RGB colors, red, green, and blue colors, into grayscale colors. I think that that's this week. And then next week, you'll actually be converting them from, or maybe this is, this is next week. You'll be converting them from RGB, which is on 0 to 255. So 256 times 256 times 256, that's several million colors possible on your screen. Because when your screen or your high definition TV or your old catheter ray tube TV, when they produce a color, what they do is they mix in a certain amount of red, green, and blue to produce these millions of different types of colors. Well, CMYK is an alternate color system. C stands for cyan, and then magenta, and then yellow. And then K is the level of black that you add to it. That's used in printing. So if you actually look at the color printer, right, you have these three colors, cyan, magenta, and yellow, and then another fourth color for black to make it darker or lighter, right? And so, for example, aquamarine. If you were to represent that in RGB, it would be these three values right here, these three RGB values. If you were to convert that over to CMYK, then it'd be these four values, if you wanted to actually print whatever was on your screen on a piece of paper using a toned printer, right? And then you're going to convert back and forth. The way that we do unit testing here is by creating an array of these things, right? And then we then we have to call this function that sets up, well, you need to call this function on this data, and then it takes care of everything. It's actually quite complicated, which is why we don't expect you to start from scratch, which is why we give you this. With this, however, you can come up with your own colors, right? We've got basic ones like aquamarine, black, red, green, blue, cyan, et cetera, Husker red, Spotify green, et cetera. So to add your own test cases, all you do is basically copy paste this code and develop your own test cases. Meaning that you would come up with your favorite color, you have your RGB value, you stick it into your calculator, right, and you manually calculate it, and this is what it should be. Then you add additional code down here to add that test case to the CMACA test suite. You just type one command, make, then you run the thing, and it comes out with all that boilerplate stuff that we wrote a couple of weeks ago of if, then else, and we add up the number of correct ones, add up the number of failing ones, then produce a summary report at the end. That's all taken care of by the library. All you have to do is come up with new test cases and then use our code as a basis for this. Right? It can get quite complicated. Right? In fact, this is already quite complicated. In order to do this, what we're going to do is give you what's called a makefile. Right? So this is yet another programming language. You can see that there are variables here. CC is equal to GCC. That means that when you use it down here, I'm defining a compiler. What compiler do you want to use? That way that you only have it in one location. I'll change that over to Clang or something like that, some other compiler, right? Then you've got your flags, your includes, et cetera, et cetera. And these are rules. How do I build this file? Well, it's dependent on this file and this file. Right? Well, how do I build that file? Well, here's the rule to build that file. It's dependent on this file and this file. And here's the command to run it. This is what we would do normally at the command line, but I don't have to type it over and over and over again. I put it into a script file called a makefile, and it takes care of it for me. Once again, we are not going to teach the basics of makefiles or the syntax or anything, but we will give you examples if you want to work off of them. In any case, we give you examples like this because it gets kind of complicated to build these things. And this is not a formal introduction, this is a gentle introduction to what are called build systems, or the people involved in that are called DevOps, development operations. Their entire jobs, whose job is not to write any code, but to write the code that compiles everybody else's code. And they maintain all of that stuff. They write a script to deploy it to production at the very end. They write a script to deploy it to testing environment, to a staging environment, right? When I was in industry, we had, I believe, like 100 different developers, programmers, and we had 2 dedicated DevOps people. We didn't call them DevOps back then, but their entire job, 2 people, to help 100 people just doing DevOps stuff, creating makefiles, creating build systems, and figuring out dependencies and stuff like that. Right. So again, it's not something that we're going to get into any deeper than this, other than if you want to, you can start making your own makefiles. At the end of that lab next week, there's a link that you can read a tutorial on how to do so. Otherwise, you can just use ours as a basis and check it out. All right. So there's our oh, and then finally, the last thing I wanted to review is that functions are passed by value. You remember what that means as far as passing stuff, right? Where I had this A and this B, 10 and 20, and then I printed them out before we called this function called swap. Right? And then we printed them out after. Well, what did the swap function intend to do? Go away. All it did was take A and place it into temp, take B and place it into A, and then into B we placed the temp before. But did it work? No, it did not work. Let's go ahead and review that. Demo.c. There we go. Let's run it. It's 1020 before, and it's still 1020 after. We're now going to start on our journey to change this so that it does work. Right? But to do that, we need something new, right? And that something new is called a pointer. Okay. So think about memory. Right? Memory in a computer has both an address and contents. So I've got a photo for you, not a photo, but a diagram here for you. Right? There it is. Right? This is in my book if you want to check it out and look at it. But otherwise, we've got up at the top here, memory consists of an address, which is nothing more than just a bunch of numbers. In this case, represented in hexadecimal. That's base 16. We count in base 10 because we've got 10 fingers and 10 toes. A computer counts in binary because that's the simplest. That's as simple as you can get it. It's either high voltage or low voltage. The switch is on or the switch is off. It's a divot or it's not a divot, right? Or whatever they are on CDs. On CDs, I think it's like that it's been poked or it's not been poked or whatever those things are called, right? In any case, it's binary. And then to make it more compact, they do it in base 16. That's 0 through 9 and then A through F to form 16 different characters. Right? You'll note here that some of this contents could just be memory, like a function, like the main function. It has a bunch of binary code to actually execute on the program. And it's not meant for human consumption over here. Right? It's just a bunch of data. Some of it is meant for human consumption, for example, like the representation of pi, which is a double, and it takes 8 bytes. You'll see that that's why it's taking up so much memory here. We've got 1, 2, 3, 4, 5, 6, 7, 8 bytes. And you don't have to learn hexadecimal here, but you can see how it works. 7C, D, E, F. Then what happens when we get to the last character? It rolls back over to 0, but then we have a carryover here to 80, right? And then 81, 82, 83. That's how hexadecimal works. We've got 8 of these things representing this large, this floating point number, this double right here. Remember that integers don't take as much space. They only take 4 bytes. So 1, 2, 3, 4 bytes here. There's another integer. And then characters, they only take 1 byte. So the capital H is stored in one location. The lowercase e is stored in another location. Now, generally, this memory is contiguous, right? It's counting up here. You can address it to the first byte, the second byte, the third byte, the fourth byte. Right? You can get individual bits if you need the fourth bit of the fifth byte. You can do that, but it requires some what's called masking and bit twiddling. We won't get into that here, though. But you would in a systems class. Right? In any case, the takeaway here is that there's address and contents. Up to now, you've only been dealing with the contents, right? But an address is a numerical designation where data is stored, right? Address is also called a reference or memory location. So we'll use those interchangeably as we go throughout, right? The contents are the actual data that is being stored, okay? And that's what you've been doing up to this point. Up to this point, when you write a program, let me go ahead. I'll keep all that for now. I'll go ahead and get rid of this, though, temporarily. Right? If I just say int x is equal, let's go with a, is equal to 42. Okay? You are only dealing with the contents of memory. Somewhere in memory, there's located a variable called a, and now we've placed in the value 42 there. In fact, let me make it match my diagram, and I'm going to put 10 in there. Okay? That picture looks like this. All right? Ignore the top one for a second. That picture looks like this. That a is stored somewhere in the contents of memory, and it has, or is somewhere in memory, at some address in the memory, and then it's got the contents of 10. Right? That's what we've been doing up till now. Okay? Now what we're going to do is something a little bit different. What we're going to do is we're going to create a pointer. Create a pointer variable. Right? What is a pointer variable? A pointer variable is a variable that doesn't refer to the contents of memory. It refers to the memory itself. A pointer variable represents a memory address. Okay? So here's the syntax for doing it. I'm still going to make it an integer, and if you wanted a double pointer, it'll be a double. We'll talk about that later. But I'm going to call it PTRA, pointer to A, all right, for short. Now the way that I do that is I place a star in front of it. You might call it an asterisk. You might call it a star. You might call it a, is there anything else that you'd call that? Usually we'll just call it a star operator, or a star here, right? That will create a pointer variable. At this point, however, what is PTRA pointing to? Question mark, question mark. Now to answer that question, I'm going to ask it in a different context that you already know. Int x, what value is stored in x right now? Who knows? It could be 0. It could be dead beef. It could be some random value, right? So same goes for this. Who knows, right? It could point to a valid memory location that doesn't belong to our program. Now think about the implications of that. What if we were able to access that memory and do whatever we want with that memory? What if there were security keys and passwords stored in that memory? Do you think that any old program that you write should be able to access any old memory that you want? No. And so there's going to be consequences to that. It could point to a valid memory location that does belong to our program. So what are the implications of that? Well, it could be okay, right? But you could get yourself into a lot of trouble. What if I just what else is stored in memory? My main function, my swap function, my sum function, my average function. What if I start changing the contents of memory that stores code? Now I'm writing a program that rewrites another program or rewrites itself, right? That is probably unsafe, right? And we'll see the implications of that later on here, right? It could point to an invalid memory location. Right? These are all just numbers at the end of the day, right? But my computer only has a certain amount of information, only has a certain amount of addressing. Say that I've only got 8 gigabytes, and I try to access the 50 quadrillionth terabyte. Is that going to make any sense? That's way too much memory, right? So it's a memory location that doesn't even exist. It's an invalid memory location. Right? So it is best practice to initialize memory. And for now, what we're going to do is we're going to initialize it to a special value here. PTRA is equal to null. You might have seen that keyword before, but it's actually not a keyword. It's a macro. At the end of the day, we can see what it looks like. There it is. What is it? Well, it's a void star. What the heck is that? We'll talk about that much later. But it's 0 basically at the end of the day. There's actually no guarantee that it's 0 when you get down to the machine code level, right? But for all intents and purposes, you can think of it as 0. But don't treat it as 0. Null is null. 0 is 0. Don't mix those two up. Okay. Yeah, question? No, not yet. We'll talk about when to use the star here in a second. But otherwise, the thing on the left-hand side is a what? It's a memory address. The thing on the right-hand side is also a memory address. They match. Right. Yeah?
What shortcut are you using to be able to see what
Oh, anything you can, well, on a Mac, it's a command. You hold that down, and then anything that's clickable becomes clickable, and you can click it. So that took me to std-def, and you can't change anything in there. I imagine. Oh, you can. Don't do that. Good luck if you do that. Don't. Yeah, I shouldn't have shown you that magic. Forget about it. But you can do it with other things like PTRA. Right? I don't think that it would save, but then it takes you back to the declaration. What else? Sum. It works for functions too. It'll take you to the sum function. Right? So anything that's clickable, it's smart clicking. Right? All right. So that sets it to null. Later on, you can do what are called null pointer checks. Right? For example, if PTRA is equal to null, right? Equals because equal is the assignment operator, then we can print out an error message. The memory is not initialized. Right? That's a way that we can do basic error handling and error checking. You cannot work with a null pointer. Right? If you try to do anything with the null pointer, it's going to end up with, as we'll see here, a segmentation fault. We've seen those before. Right? When we forgot to put an ampersand in front of something when we were using scanf, it ended up with a segmentation fault. A segmentation is a segment of memory. A fault is an illegal operation. We tried to access memory that illegally, that didn't belong to us or doesn't exist, and so the operating system detected that and killed it with an error message. Right? All right, so you can check basically looking before you leap. Now let's make it point to a valid memory location, because that's what we're going to want to do. We want our pointers to point to valid memory. So PTRA is equal to X, or not X, but A, sorry. Now that's wrong. Let's understand why it's wrong before we fix it. The thing on the left-hand side, what was that again? That's a pointer. The thing on the right-hand side, what is that? It's a regular old variable. In fact, that's what I usually call them, right? A is a regular old variable. It's not a pointer variable. So do these two things match? Just like if you had an integer on the left-hand side and a double on the right-hand side, they would mismatch and you would end up with integer truncation. Or if you had an integer on one side, or like a character on one side, on the right-hand side, and you tried to force that to become an integer, it probably would be bad too. Like capital H would end up having whatever the ASCII text value is. So these are incompatible. What I have to do is I have to make the right-hand side into a pointer, right? And the way that I do that is with the ampersand in front of it, right? Do you remember where we saw ampersand? With scanf again, right? That's why we put the ampersand in front of it. It takes the variable and it changes it into a pointer by getting the memory location of that thing, right? All right, because if I didn't do that, let's look at the consequences here. GCC demo with the full warning flags on, and it's telling you, it probably does this even without the warnings, wait a second, the assignment from a pointer to an integer is probably not valid, probably not something that you want to do. Okay? But when I put the ampersand in front of it, now the thing on the left-hand side is a pointer, the thing on the right-hand side is also a pointer, so they are now compatible and there's no warnings there. Okay? Here's a picture of it. Now we can look at the entire thing here. Right? Initially, PTRA is also stored somewhere in memory. It has an address, but its contents is null because it is pointing to nothing. Right? Now what I've done here is PTRA is equal to ampersand A. What that does is it goes out to A, gets the memory address, which is 26EC84, just some memory address that we don't really care about, and it places that into the contents of the pointer. The pointer is now referencing this memory location, which has the contents of 10. Right? So a little bit more complicated than just working with regular old contents. You might ask yourself, why the hell do we need this? I could just, if I wanted to reset X, or A in this case, to 20, I could do it. Why do I need a pointer? Hold on to that thought, right? It solves all the problems. It solves the swapping problem, right? All right, but in any case, let's make sure that it actually worked. Printf. A has is a regular old variable, a regular old variable, and it is stored in memory location, percent, question mark, I'll come back to that and we'll fill that in, and has the value %d because it's an integer. %d is still the placeholder for an integer here. Now, what's the placeholder going to be for a pointer? I'll give you a hint. It makes sense. Just like the character makes sense, but the integer and the double don't make sense. It's p because it's a pointer, right? Now, how do I get the memory location of a? Well, we just said ampersand a and a. So the memory location is ampersand a. The value is going to just be by itself a. Right? Now let's print out information about our pointer. Printf. PTR a is a pointer variable. And points to location %p. I'll end the line right there. And PTR a. Now remember, we made PTR a point to a. So those memory locations are going to match up. GCC. Let's run it. There we go. Let's clear this out and give myself some more room there. There we go. A is a regular old memory variable, and it's located in memory location blah, 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 blah. Right? And it has a value of 10. PTR is a pointer variable and points to the location blah, 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 but guess what? That blah, blah, blah is the same as this blah, blah, blah. Right? Because it's the same memory location. Okay? By the way, if I were to run this again, do you think that you would get the exact same value there? Let's find out. Same? I mean, the two match because they're pointing to the same location. But the first run and the second run, are those the same? Nope. Third run, is that the same? Nope. 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 What's going on here? Remember, when you run a program, what happens to the program a.out? That's stored somewhere on disk. When you run it, what is that thing? That's a bunch of dishes? It's the call stack. Let me pull up my picture again of the call stack here. I need to pull it up. iCloud. Where's the memory stack here? Here we go. Now I'll bring it over. What's the very first thing that gets placed on the call stack here, the memory stack? Your program code, right? Now, it's very, very unlikely that when you run a program, it's going to be loaded up in the exact same memory location as it was before. Right? Astronomically, the odds are against you. Because when you think about an actual system, right, pull up the task manager in Windows and see how many things are actually running. Top. This is the task manager here, kind of. Right? Top tells you everything that's running at once. Well, it looks like there's some process that's run by the Ubuntu, its Node, and it's using 42 gigabytes of virtual memory. It's about 6% of all the memory. That's about 2% of the CPU, right? If I were to actually run a program, a very, very computationally expensive program that was running for hours and took a lot of memory and took a lot of CPU time, then I would see these numbers jump here. Right? We can look at this on a much larger system since this is a virtual system. I'll go to Neuros here. Neuros is the server that you have access to do your PDC modules that I've mentioned before that need to be done by November. So you don't have to start on them right away, but you definitely should have that in the back of your mind. You'll run HTOP maybe if you do everything. And here we've got 100, these are all the cores, 0 to 127. So there are 128 cores on that machine. I don't think it's downstairs anymore. I think it's over in the engineering buildings. I'm not sure where they put all that stuff. But there I am at the top, running HTOP here. A bunch of people. These are just people on the system that are running things at this time. I don't know. It looks like somebody's running Java right there. Somebody's running some Python stuff at some point, right? And you see what they're all taking. Like that one has 428 megs of data, and it's using 31%. Oh, now I'm using 37% of one CPU, right? Just running this top demonstration right here. And then you can see it going in and out. In other words, the takeaway here is that there are thousands, if not millions, of little tiny processes and programs running all at once on the same system. Right? Each one of them is grabbing a piece of memory When it's done using it, it gives it back to the operating system, and the operating system makes it available for other processes. So since you have all of these programs coming in and out of existence, the likelihood that any one of them gets loaded up in the exact same memory location as a previous run, it's infinitesimally small. If it ever happens, you basically used up all of your luck instead of playing the lottery, right? Oops, I don't want that, right? Let me run it again and show you that no matter what, right? I could run it run really quick, right? And that's as quick as a human can do it. And it's not going to be loaded up into the same memory location, right? So that's why we're getting different memory locations for each and every one of these, okay? Now, let's manipulate the contents of memory through a pointer. Right? You can do that normally. You can do that directly. What if I were to say A is equal now 20? Everybody's done that in this course now over the last couple of weeks. Right? You know how to do that directly. Right? How do we do it indirectly through a pointer? Right? So PTR-A is now equal to 20. That's incorrect for the same reason that it was incorrect before. What's that thing on the left-hand side? It's a pointer. What's that thing on the right-hand side? It's an integer. Right? Are those the same thing? Nope. So to make this compatible, this is now where I put the asterisk in front of it. This is what's called a dereferencing operator. A star in front of a pointer variable makes it into a regular old variable, so you can set its value. Right? Star in this case is a dereferencing operator. Right? It's an operator just like the ampersand was an operator. That's called the referencing operator. It gives you the memory location. This one takes a memory location and forces it to become a regular old integer so that you can now set it. Let me go ahead and repeat this code down here to see now that it has changed to 20. But the memory location has not changed. Right? Before it was 10, now it's 20. Right? But it's still stored in the exact same memory location in all four of these. Okay? Here's a picture of it. Here's my last picture over here. Sorry. There you go. So when I dereference the pointer, I am jumping from that pointer to the memory location, and then I am manipulating the contents of that memory to 20. Okay? All right. So again, why would you want to do this? Hold on to that thought for just one more second. Let me show you some consequences. Bad things can and will happen. ... Having access to the what we call the wire or the metal, right? In other words, the actual memory contents, that's something that's very, very unique to C and to an extent in C++. Most programming languages do not allow you to do this for one of the reasons that I stated before. With great power comes great responsibility. Can you access arbitrary memory locations? Well, you can try, and if the operating system is written well enough to detect that it should not happen, it won't happen. But what if there's a bug in the operating system that doesn't catch that? Or you can write code that circumvents those checks to get into memory locations that you shouldn't be getting into, right? Now you have a potential security issue. You can do code injection, you can do memory dumping, you can grab another person's memory and dump it and then analyze it and look for security keys, passwords, whatever you want, right? So we're hoping that the operating system is written well enough that it always detects these things, but bad things can still happen. For example, example 1, right? Set a pointer value to an arbitrary location. So PTR-A is equal to, PTR-A is equal to 42. There is no star operator on the left-hand side. I am not dereferencing it. The thing on the left-hand side is a memory address. The thing on the right-hand side is not a memory address, but it's going to let me do this. What is PTR-A now pointing to? PTR-A now points to memory location, what? 42. Does that memory location exist? I have no idea. Right? Let's find out. GCC, it's going to give me a warning about that, right? I don't think that this is what you want to do, but go ahead and proceed with caution. There are no consequences here because all I said was make it point to that memory location, whether it exists or not. I'm not actually going to that memory location and trying to manipulate the contents or read the contents or do anything. So let's go ahead and do that now. I'm going to do that by taking this. PTRA is a pointer variable and now points to location %p, and I'll output what's actually there, which stores value %d, and then I'll dereference PTRA. Now I am actually going to the memory location because I'm dereferencing it. I'm grabbing the contents of that memory, whatever it might be, and I'm trying to print it out. Now predict what's going to end up happening here. Does memory location 42 exist? Maybe. Right? Does it belong to me? All likelihood, no. Right? And so we get a segmentation fault. That's exactly what would have happened if you had forgotten the ampersand on scanf. Right? Another bad thing that can happen. Let's say make PTRA point to a location that you own. But it will cause problems. So PTRA is equal to, and I will reference A here. That's memory location that belongs to me. But what I'm going to do is I'm going to subtract, say, 10 off of it. Right? This is called pointer arithmetic. Remember that a memory address is nothing more than a number. So if I get the memory address of A, and then I jump back 10 locations, that's like going from here down to here, or about thereabouts, whatever 10 is. Right? All likelihood, let's kill that. I don't want to look at that anymore. There we go. All likelihood that memory does belong to me. Right? And let's go ahead and try it. And it's going to, here, let's get rid of this first, because this is dangerous. I want the program to survive at least up until that point. No consequences unless we start manipulating the contents. So let's go ahead and change the value of whatever is stored there to, 42. So here I will dereference it. PTRA is now equal to 42. So what ends up happening here? Oh, come on. Nothing. At least in this case. Nothing happened because it didn't detect that there was any critical memory right there. All I did was screw up my own memory, right? No segmentation fault, but we likely screwed up our own memory. The operating system is perfectly fine with that. It's your memory after all. You can do with it whatever you want to do with it, right? Now I'm going to try and forcibly screw it up, right? So what I'm going to do is I'm going to say PTRA is equal to main. And I will say PTRA is now equal to 1, 2, 3, 4. We'll get into this much later. Main, that's my function, right? How can I use that without calling it? Right? In fact, some people have made this mistake very, very early on, and it compiled, and it wasn't working, and they were wondering, well, how can I do that? The name of a function, well, where is a function stored? Or where's a function stored? In your stack. Where's your stack stored? Somewhere in memory. Main, wherever the main begins, that has a memory address. And so what I'm doing here is I'm changing the main code to 1, 2, 3, 4. Actually, I'm only changing the first 4 bytes of the computer code that defines main to 1, 2, 3, 4. What happens now? Most definitely there's going to be a problem now, hopefully. Yeah, segmentation fault. I wrote a program that overwrote itself, right? And that's what's happening here. The operating system detects that something screwy is going on here. Usually it ends up with what's called a stack smashing event. Because remember, you have this stack here. If you go and pull out that dish from the bottom, you've smashed your own stack and it all comes crumbling down. The operating system will detect that and end the program with an error or a fault. Question? Yeah, go ahead.
The way that it gives you your memory location,
Mm-hmm.
if you were to like put that equal to something, is there a way you can do that in the code? Like just like
Oh, like you want to know the memory location of main?
yeah.
Okay, we could do that. We're not going to actually access it, so we can print off main is located at memory address %p and the line, and it's PTRA. There. Or I could just substitute it in directly main. Or another way, a more verbose way of doing it would be an ampersand in front of it, but that's not necessary. I'll just go with PTRA right now. I believe that it will be completely fine with this. Yep. There you go. So my main code is actually located there, and then my variables are located way, way off. I don't know why. That's all system specific. That's all operating system specific. But yeah, you can really screw things up. Right? You can screw up other people's memory, but you can try. But ultimately, it will end up being a segmentation fault for most of the stuff. Okay. All right. Another bad thing. Other bad things. Right? Dereferencing invalid pointers. So let me go ahead and reset pointer to A, and remember that initialization null. Right? We did a null pointer check. If it's null, we don't do anything. But what I can do here is I can say, oh, okay, let's go ahead and dereference PTRA, and I'll set it equal to 42 there. It's pointing to nowhere. Can you put 42 into nowhere? Nope. So this is also going to be a segmentation fault right there. Right? There was no segmentation fault up here. Dereferencing invalid pointers, this is going to be bad, and it results in a seg fault or segmentation fault. All right. Now again, why do we want all of this? Well, if instead of passing by value, I pass the memory addresses of A and B, then I could jump to those memory locations and directly manipulate the contents and swap them out. We'll cover that starting next time, but I do want to show you a nice little reminder. I call it a mnemonic device for remembering that you cannot dereference a null pointer. So let's go with Bret Hart. He's a wrestler. Right? Bret Hart dereference null pointer. And I don't know if I have audio on this or not, but we'll find out. There we go. So before this plays, there we go. Back in the 90s or something, right, there was a wrestling game that was released, and part of the promo is that they shot this video of these wrestlers going in with the developers and working with the developers. And Bret Hart here apparently knows programming because, I don't think I can get the audio in the room, so I'll transcribe it if you want. But
come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
There you go. So, anytime you find yourself with a seg fault, you probably dereferenced a null or invalid pointer. Hit yourself, remember Bret Hart, and hit yourself over the head, and come back and fix it. Right? So, maybe we don't like wrestling. I always found that hilarious, though. Right? No? All right. 80s and 90s wrestling. I haven't watched wrestling in years, though. But that's a good way of remembering. Just remember Bret Hart, hit yourself over the head, and don't dereference null pointers there. Right? All right. We'll pick it up there next time.